All right, so what is the computer algebra of the system of the future? Well, first of all, what is a computer algebra system? I want to say that a computer algebra system is a way to reason about mathematics using syntax and also facilities for some amount of automated reasoning. It's not full automated reasoning, but it's a mix. And then two, why do we care about computer algebra systems? Well, we want to do math on a computer and we don't want to do it all ourselves. So hopefully, when we're doing numerical analysis, when you actually want to solve differential equations, when you want to build scientific models, then of course you can just write all the code yourself. But ideally, the ideal interface should look like is instead you declaratively describe your system, and then the computer figures out how to compute it for you. I mean, that's the computer's job. So here are some properties of what I think the computer algebra of the system of the future should have. These are some properties that the computer algebra system of the future should have. So first of all, in a traditional computer algebra system, the basic primitive is like a syntax tree. Like this is what it would look like in say, Mathematica, where it's an untyped term with free variables. And this is a very powerful paradigm. Like Mathematica goes incredibly far with this paradigm of I'm just going to rewrite these untyped terms. But there are limitations. Namely, some of the limitations come from things that you actually want it to do. But some of the limitations come from just it's when you as the user want to use this system, then the fact that you can't express all of the math that you know in the system makes it confusing. Like, what are the types of these variables? Well, I don't know. In this case, they're just symbolic. What are the operations that we can do on these variables? I don't know. And then also, this is sort of a little bit of a technical point, but this is something that logicians, when you read a first-order logic textbook, you spend half of your time, half of the rules of first-order logic are related to manipulating terms without having clashes of variable names. So it's we can do better than this. So the idea is that in a morphism-first computer algebra system, the basic primitive is a morphism in the Kleisli category of a syntax monad. And I'll get into exactly what this looks like in a later slide. But the problems that this solves is that first, the types of all of our variables are given by the domain and codomain of this morphism. Secondly, the algebraic theory, the operations that you're allowed to use, are given by the monad that we're using. And finally, substitution, all of this annoying, nasty renaming stuff, that's just morphism composition. Now it's like a well-behaved, rather than some weird, algorithm where you walk through the terms and replace it. No, it's built in. It's just morphism composition. Another property of the computer algebra system of the future is that when you are working in an algebraic theory, you should have functorial semantics for that algebraic theory. So you should be able to declare a model of that algebraic theory, and for free, you should be able to interpret your syntactic morphisms in that model. And traditionally, sort of doing this, having models of syntax is hard because computer algebra systems are written in high-level dynamic languages, which is convenient for experimentation and sort of the types of exploration that you want to do in a computer algebra system. But then when you go to do the numerical the numerical computation, you go to a low-level compiled language like C or Fortran or something. But this is sort of like what I said at the beginning. What is a computer algebra system? Well, it's a way that you should be able to declare things and then get something fast out that's better than writing it by hand. So you really should be able to just interface these seamlessly. And this is well, I'm going to talk about this more when we get to what I've actually been working on. But the last thing that I want to talk about before we see what I've been working on is nonlinear syntax. So in a traditional computer algebra system, terms of a theory are represented using syntax trees. Syntax trees are like very flexible, and they're sort of a good default, because you can do, when you have an algebraic theory, you express that algebraic theory in terms of operations and relations. And syntax trees are like that's what you, like the syntax trees are free algebras. That makes a lot of sense. But often in specific theories, you can do better. You can make syntax that is like a wiring diagram or a Petri net. Or, I mean, there's lots of examples throughout applied category theory where we managed to make a graphical syntax. And one of the advantages of graphical syntax is often like equalities that had to be manually specified for the equalities that had to be manually specified for syntax trees, like associativity, come very naturally in a graphical syntax. Like in a wiring diagram, you just write 3 wires next to each other, and there isn't even a way of specifying like that. So graphical syntax can also serve as sort of a semi-normal form. And a computer algebra as a system of the future should allow you to natively work in this stuff. You should just be able to draw this stuff and work with it. So let's talk about the progress of the Topos Institute towards the computer algebra system of the future. So the project that I've been working on recently is called GATLab, because it's built on generalized algebraic theories. And it's the next generation rewrite of the core of CATLab. So it's also a bit of a pun. And GATLab is a category theoretic computer algebra system in 2 senses. The first sense is that we manipulate theories of categories. So we manipulate, like it's a computer algebra system for doing category theory. But the second sense is that it's a computer algebra system that's organized by category theoretic concepts. So morphisms, nonlinear syntax, functorial semantics, etc. So let's look at what this looks like. Let's make this a bit bigger. So here we have, so this is all code that runs. We declare the theory of a groupoid. We have objects and morphisms, and then these are our 2 types. Notice that the type of a morphism depends on 2 objects. So the generalized algebraic theories allow you to have dependent types, as opposed to algebraic theories, which just have a set of types. Then we have our term constructors, which are the identity, composition, and inverses, because we're working in a groupoid, we have inverses. And then finally, we have all of the various rewrite rules or axioms that you have in a groupoid. And courtesy of Chris Brown, we have a very nice, pretty printing for a theory, which draws all the, which writes out all of the rules in natural deduction syntax. And now we can declare morphisms in the context of a theory. So this is a morphism between two contexts in the theory. The first context is the context that has an object and an endomorphism of that object. And the second context has two objects, a morphism from x to y, and then an endomorphism of y. And this is a Kleisli map, so it sends A to the term in this context, just given by x, and it sends F to the term in this context of G composed H composed inverse G. And so this is algebra is dual to geometry. So this is a map going from this context to here, but when we actually apply this using a model, we go the other way around. So that's where the syntax comes from. We're going to take actual values in this context and then produce values in this context. But before we can do that, we need to declare a model of the theory of groupoids. We're going to use the model GL, so the objects of this are integers, and the morphisms are invertible square matrices. So this is maybe not the best groupoid because it's just the coproduct of a lot of groupoids stuck together, but it's a coproduct of a bunch of groups stuck together, but you know. So we have some dynamic checks. So we're implementing this in Julia, so you have to instead of embedding this in like a proof assistant, we just use dynamic checks to check that our objects and morphisms are valid. So objects are integers, morphisms are matrices, and the check on a matrix is that the domain is equal to the codomain, so it's a square matrix, and the determinant is non-zero, so it's invertible. And then we have definitions for composition and inverse. Oh, I forgot to put the definition for ID. Whoops. This is all, there's not much checking right now. This is all quite new, so it's just I'm getting it working, and then I'm going to put in all the checks so that, yeah. But anyway, I declare GL as a simple model of groupoid using the implementation in GL-impl. And then finally, you can see here, so here I'm interpreting this symbolic map conjugate using this an instantiation of the codomain context for conjugate, which is two objects and two morphisms, and then I get an object and a morphism. This is if you flip and then rotate and then flip again, that's the same as rotating in the opposite direction. It's a classic example of conjugation. So we're going to head back to the presentation now. Oh dear. Okay. I'm going to, there we go. So there's a lot of other stuff that I didn't demo. So one thing is that we not only have morphisms between contexts in a theory, but we have morphisms between theories themselves. So for instance, there's a morphism from the theory of categories to the theory of groupoids, so that any model of the theory of groupoids, you can also treat it as a model of a category. And you can also push out theory morphisms. So if you have the theory of sets, there's a morphism from the theory of sets to the theory of monoids, and there's a morphism from the theory of sets to the theory of abelian groups. And if you take their push out, you get what we call a pre-ring, which is a ring, but it doesn't have distributivity. So you can write down the theory for a ring by pushing out these two theories and then adding distributivity. Then we have, well, I thought Ed would be here, so this is really for Ed. I don't know if anyone else really knows what an E-graph is.
In the corner office doing deals.
But then also parametric models. So you can have like a model of a theory that is parametrized. And this allows, for instance, generic constructions for slice, para, lens. So you, like given a model of a category, you can automatically get like the para construction on that. You can get slice construction. Also, we want to do a tactic systems for rewriting so that you can prove equalities in a theory, and optimization and compilation of extracted programs to make them run really fast. Evan has a very nice theory of double Laverre theories, and hopefully that will allow us to declare, for instance, monoidal categories, and sort of and get not just a one category of models, but a two category of models. And finally, integration with Semagrams, which is a tool that I have built for dealing with nonlinear syntax, which is currently not integrated with GATLab, but can still do some cool things. So for instance, we can draw directed wiring diagrams. So I can make some boxes, and then draw wires between them. You can't see that, but it's a wire going to the outside box, but that for some reason is cut off by the TV. We can name the boxes Cass. And then, I'm going to need to, I want to go back. We also have support for Petri nets. So we can draw some boxes and wires, hook these up, and you can see that it shows the mass action equations, and it updates them as you update the Petri net. So if we add another species here, we put here, and we can name these. So let's say maybe wolves and sheep. I guess we would really want 2 wolves coming out and 1 wolf coming in. Oops. Well, there's a bug. Anyways, so we can do. We want 2 wolves coming out, 1 wolf coming in. Yeah. Yeah, we could name it wolf. It should be sheep. Wolf. Yeah, and then this could maybe be alpha. Yeah. Yeah, so sheep wolf. Yeah. And yeah, that's it. It's the computer algebra system of the future.
Can you say more about how you're going to integrate like the combinatorial syntax of like wiring diagrams or Petri nets that you showed with the more traditional tree term tree-based approach? Do you have a plan, or do you have ideas of it?
Couple things. So one interesting thing that I've realized is that it's not always a one-to-one mapping. For instance, directed wiring diagrams don't show up naturally as terms. Rather, they show up naturally as morphisms, specifically symbolic morphisms, because you can think of a directed wiring diagram as a prism in FinSet. And so you could think of that as like a lens in FinSet op. And really what we're doing here in the computer algebra system of the future is that we're working with symbolic functions as the dual categories of Kleisli categories for syntax monads. So a wiring diagram is a sort of a symbolic lens.
I see. So it fits into your perspective on these like Kleisli.
Yeah. So like, it's a symbolic lens in the Kleisli category for the identity monad, because wires only you can only sort of route wires. You don't have any operations. You don't like add wires together or whatever. And then like Petri nets sort of act in a different way, which is that like a Petri net is a presentation of an algebra for a certain monad, because C-sets are you can think of C-sets as an algebra for a certain monad. So Petri nets fit in a different way. So often there isn't a unified story for graphical syntax. Like graphical syntax is always sort of ad hoc.
I think that's sort of an open thing in the field, is trying to have
Yeah.
more,
But the hope is that like Semagrams is a generic UI paradigm.
Yeah.
And the hope is that we can develop like different classes. So for instance, directed wiring diagrams, there are lots of different variations on directed wiring diagrams, undirected wiring diagrams, and sort of be able to integrate. There's not going to be a unified solution for this, but the idea is like to integrate each of these different like classes of nonlinear syntax, be able to build out general functionality so that it's not too hard to integrate each of these like especially. Yeah.
I had a question that's probably a dumb question, which is like when you mention rewrite rules, are you thinking of those as directed or undirected rewrite rules?
Excellent question. So there's this. So this comes to the egraph thing. There's this sort of technology for doing non-destructive rewriting, where when you apply a rewrite rule, you don't you just add the result and say that these two things are the same, instead of like in traditional rewriting, you start with a term and you just apply the rewrite rules until you get to a normal form. And so these things, which are called egraphs, allow you to just apply rewrite rules and but remember where you've been before. And this helps with some stuff, like for instance, if you have a rewrite rule which is like A goes to A compose the identity, with a traditional rewriting system, that blows up. With egraphs, that actually terminates after one step, because it just says A is equal to A, compose the identity, and then it sees that it doesn't apply that rule anymore.
You have to tell it not to do it, right?
Well, it can detect that it can detect that like I've already put this rule in, and that rule already, like the fact that equality is in, that already implicitly contains like A is equal to A, compose the identity, compose the identity, compose the identity, because then once that's in, it sort of implicitly contains the fact that you can substitute them. So egraphs make dealing with theories where there aren't normal forms under rewriting possible. It's not if you have a normal form. For instance, if you're doing commutative algebra, you don't want to mess around with egraphs. You want to go straight to Grosvenor bases, right? Or like if you're dealing with monoidal categories, you might want to use wiring diagrams instead of egraphs. But egraphs sort of give a there's sort of a sledgehammer approach to dealing with these kind of problems that you can sort of fall back on. Yeah.
I was just going to ask, the monad that your Kleist morphisms are living in, is this like the free algebra on a context?
Exactly, yeah.
Yeah, you're on what?
On a context.
What's your context?
A context is like a collection of generators.
Generating
So like
syntax trees?
yeah.
Like little Corollas type of?
Like the idea is say you're working in the theory of categories, then a context would be like, I have these objects and these morphisms and of these types. It's kind of like a free category.